Great. Great. Thank you for the invitation to be here and speak today. So I'm Trevor Boyer. I'm a professor of environmental engineering at Arizona State University, and I'm going to be presenting on work we do related to urine separation. And the motivation, as you'll see, is for nutrient recovery, and I think pairs well with a lot of work that others are talking about here today. As good students are what accomplish all this work. Lucas is here, fortunately. He's in the back of this picture here, and he'll be able to, kind of during breakout sessions, talk about some of this urine work. A lot of this is funded right now by STEPS, which is an NSF Science and Technology Center focused on phosphorus sustainability. So in terms of urine, the big picture would be that if we think about our wastewater systems and, a building like this, for example, from a volume perspective, most of the water leaving this building is, essentially gray water. So the blue and the black there, flush water, gray water, and some very small volume, around 1% is the actual liquid human urine. However, if you do a nutrient balance on that, so mass balance is here along the bottom, most of the nitrogen that originates in wastewater is from human urine. About half of the phosphorus, half of the potassium as well in the wastewater originates from human urine. And then not really going to talk about it today, but most pharmaceuticals that we take also sequester or partition into the urine phase. So I think, from a volume and mass balance perspective, there's a lot of favorability to this idea of separating urine at the source and using it as a source of nutrient recovery. And so we've been pursuing this topic for a while, and there are different motivations. What I'll focus on today is the nutrient recovery potential. There's actually big water conservation benefits by doing this, and that's because you want to collect undiluted urine. So you want to have waterless urinals, you want to have urine diverting toilets, and in a building like this, that can equate to like 25% water savings. So water conservation. If you do all this, it should lead to improved, source water quality. There's modeling studies that have looked at the performance of wastewater treatment plants in conjunction with urine diversion, and you can make wastewater treatment plants themselves work more efficiently from a nutrient removal perspective. And then there's the pharmaceutical piece as well. Again, you could do upstream management of pharmaceuticals instead of, advanced wastewater treatment. In the context of what a lot of us are interested in here today, from an NPK recovery potential, these are some of the products you can extract from urine. And, working with Jonas, for example, you could do even more creative things. So from a nitrogen point of view, you can capture urea, ammonia, and you can make, compounds like ammonium sulfate, ammonium nitrate, ammonium bicarbonate. With phosphorus, you can create phosphate solutions. You can also precipitate different, phosphate minerals. Struvite, magnesium ammonium phosphate, calcium phosphate are the sort of most obvious ones, but lots of others. And there's the potassium as well. You can create sort of a mixed potassium chloride, potassium sulfate salt. And these are just sort of the most obvious forms of nutrients that can be captured. And so today, what I want to think about is it's a little different. It's more thinking about how we can kind of create this resource recovery factory and then, pair with others doing even more kind of advanced technology development. So the questions that I'll quickly go through today is this idea of, how do we actually implement urine diversion? I mean, to me, it's always been sort of a compelling argument, but the implementation still has some ways to go. And so not only how do we implement it, but then where should we implement it? It definitely doesn't make sense everywhere, but sort of as a corollary, there are some places where it really does, I think, make sense. And then we see there's sort of a two-phase here. Implementation is a technology or a technical approach and a social component. And then there's the actual adoption of you get these systems in and they need to be sustained. Really quick background. We've already heard a lot about urea today. For us, or for human urine, if you haven't thought about it or don't know, after water, urea is the second highest concentration component in human urine. Human urine is essentially a urea solution. And urea is an active molecule, right? And most bacteria can hydrolyze urea into ammonia and bicarbonate. And so in urinals and in toilets, this will happen, or in the wastewater collection system. And so, the telltale signs of urea hydrolysis are an increase in pH, an increase in conductivity. And then in urine and other waste streams, when that happens, especially that increase in pH, you're going to see a decrease in things such as phosphate and calcium magnesium precipitation. And so from a nutrient recovery perspective, A, we may want to recover urea, so we want to control that process. And B, we often want to recover phosphorus. So controlling and managing urea hydrolysis is a big focus of what we think about in urine separation. And so one of the first things we did was created this urine diversion test bed because this is what we want to be able to do in these types of buildings. So why not really study this carefully in the lab first? And so these are waterless urinals where we would essentially replicate the urea hydrolysis process so that we can understand it and control it. And this is just an example of the results of some of these experiments. So the data are taking samples from the drains of those urinals. And what we wanted to simulate here was what we called sort of low urination frequency and high urination frequency. So, think about a building like this. I don't know if this building is going to be busy today or not. But you go around campus, right? And there's places on a campus that are very busy. Someone is coming in and out of that bathroom constantly. Whereas you have other buildings with sort of less people using it. And it turns out that the sort of hydraulics of that intermittent flow have a big impact on the urea hydrolysis process. And we were able to show that under sort of this low frequency scenario, urine sits in urinals and drain pipes and hydrolysis proceeds. Whereas in a sort of higher frequency environment, you have almost like a continuous flow of urine. And so the hydraulics are faster than the actual hydrolysis process. So that, makes sense from a fluids type perspective. And then overlaid on that is we want to control the urea hydrolysis. And so for us, the approach that we found most effective to controlling urea hydrolysis is lowering the pH. There's other ways to inhibit urea hydrolysis, but they're not compatible with the chemistry of human urine. So we've found acetic acid addition to around pH 4 or 5 is the most effective for controlling urea hydrolysis. And what we've been doing, as I'll show sort of since then, is continuing to sort of scale up this process to make it work in a building like this. This came up with a conceptual model for us of, again, how do we control urea hydrolysis? And, the variables are things like occupancy and time spent in a building. Simple variables, but they're important for how you would actually implement a system like urine diversion. So we then went from sort of the controlled lab to something that we can control but still be realistic, and that's our urinal on wheels. And so this would be moved into actual bathrooms. It's a waterless urinal. And then, behind it, you can see we have a storage tank, we have sensors, so we can monitor pH, conductivity, temperature. We've tried to do different ways to actually count the number of people who are urinating in this. And we can do controlled experiments. We can do controlled experiments where we let hydrolysis progress, and we can do experiments where we want to inhibit hydrolysis. I guess I just want to kind of reiterate two things. One is that everything I show here is urinal centric, and that's for the main reason is because waterless urinals exist in U.S. plumbing code. There are urine diverting flush toilets that exist. They are not compatible with U.S. plumbing codes. And from Lucas and I's experiences, there would be a big sort of social educational piece to those two, because even for this type of work that we do with waterless urinals that have existed for decades, we still get a lot of kind of occupant pushback. There are still people who find waterless urinals, revolting. And Lucas and I could tell you stories about that. So making the jump then to urine diverting toilets is something I would love to see, but that's going to take an even larger kind of social component. But I do think all the results we've generated for waterless urinals are directly applicable to urine diverting toilets. I mean, urine diverting toilets, to not get too far away from this topic here, is essentially a kind of a urinal and a toilet combined. The urine collects in the front of the toilet, and feces and flush water go to the back of the toilet. And again, the other thing why this big focus on sort of urea and urine collection right now is because that's step one. If you can't effectively do step one, if you can't manage urea versus ammonia, if you can't prevent phosphorus loss, then all the nutrient recovery potential disappears. And so based on sort of our conceptual model of urea hydrolysis and thinking about how buildings actually, commercial and institutional buildings behave, we looked at different acid addition scenarios. So runs 1 and 2 are no acid addition. And so when you collect urine in any sort of quote sort of natural or built environment, urea hydrolysis is going to happen, right? Bacteria are everywhere on us and on all objects. Most of them carry the urease enzyme, and so urea hydrolysis will happen. And we know that when we see pH go to pH 9. Urine is buffered at pH 9 because of the ammonia and the bicarbonate. So then thinking about, again, how buildings are used, how people occupy buildings, we did different scenarios of acid addition, either acid addition after every user, acid addition during the day. We had some sort of rationale for that, acid addition during the evening. In all cases, you can see we're maintaining pH of around 5 in all those acid addition scenarios, which from our experience is able to keep the total nitrogen as urea. And this was, again, with just, in a bathroom with people, because we've interacted a lot with, maintenance staff. And in order for this to be a reality, urine diversion, it's got to be seamless for occupants, for people using the bathroom. It's got to be seamless for staff. It's just got to be the same, except you happen to collect urine and recover products from it. Just highlight a few things. So the urine collection is step 1. Urine storage would be step 2. And that's where you start to make decisions about, do you want to recover urea? Do you want to recover ammonia? How do you want to recover the phosphorus? And so I just highlight here sort of how the urine changes over time. And what you see in the upper left there with pH is that over time, the stored urine does hydrolyze. We're looking to sort of reversibly inhibit the urea hydrolysis. Maybe we want to keep it as urea kind of forever or until we process the urea. Maybe we want to let it hydrolyze to ammonia to create some ammonia product. So storage time, we looked at storage time in terms of how hydrolysis progressed. And then over here on the right, you can see both ammonia and phosphate. And I mean, essentially, if you were to kind of pair, in some cases, we maintain a low pH, we maintain low ammonia, we maintain low phosphate. And, not surprisingly, those are the conditions where we added the most acid, right? So you add the most acid, you maintain conditions that prevent urea hydrolysis. And again, this is all the things that we're trying to kind of be able to understand and generalize for a building like this. And the reason I say building like this is because our focus is on, commercial and institutional buildings. I'll show you, I mean, it doesn't quite make sense in our opinion to do this at the household level. The sort of nutrient recovery potential is not really there. But commercial institutional buildings, this makes a lot of sense. And so you're gonna separate the urine, and then you're gonna collect it and store it. And then how you sort of design that system is going to dictate, again, whether you're in a position after some amount of storage to recover ammonia or to recover urea or have the phosphorus in a specific form. Couple slides on sort of some of the nitrogen recovery technologies we've looked at. Urine starts as urea, as I've mentioned, and if you let hydrolysis occur, then then you can have ammonia. And we've looked at membrane separation processes like forward osmosis, nanofiltration, reverse osmosis, and just a couple slides. So, I mean, in one case, a while ago, we explored using forward osmosis as a way to separate ammonia. With forward osmosis, you need to have some kind of draw solution. So there we had an acidic draw solution. So ammonia passes through the membrane and then is acidified into ammonium, and now it can't back diffuse through that membrane. So this could be one creative way to capture ammonia from human urine. And if you have sort of a draw solution that could also have some value, then your actual product is created there in the draw solution. The other thing is looking at urea recovery by things like nanofiltration or reverse osmosis. When you typically think of RO or NF, it's, you permeate the water, that's your product, and then you have a concentrate, that's your waste stream. Urea is a small neutral molecule, and so it's going to permeate the membrane like water does. And so you're actually wanting, or our approach was we were wanting urea to permeate the membrane, and so that our product was, say, a urea water product of very high purity, and then all the salts and organics would be rejected by the membrane. And so there's a trade-off between sort of urea permeation and conductivity. And so the trade-off is you can get a very pure urea product, but you are not sort of getting the maximum amount of urea recovery potential. Or you could get you could get kind of a high level of urea recovered, but there is going to be some salts. And so maybe from a fertilizer point of view, a lower purity urea product is okay, and you can process it further. For some industrial uses of urea, you need a very high urea quality. And so there you're maybe willing to sacrifice not being able to recover as much of the urea, but you're producing sort of a high value, high purity product. And then, my student Hannah, former student Hannah, just made sort of a decision tree of you start with urine. And what you have to recognize is that you have to decide sort of at step one or step zero, do I want a urea product or do I want an ammonia product? Because the entire system design and operation is gonna sort of follow from there. So then I had the sort of good luck of when I was joining ASU that a building was being built in its sort of final architectural phase. And I was able to convince the architects to implement urine diversion for the urinals. And so I worked with the plumbing designer, and it's a 5-story building, has one restroom on each floor. And so the urinals are on this pipe right here. So all of the urinals connect to this pipe, no sinks, no toilets, no other water connects to this pipe other than the urinals. It goes to a janitorial closet on the first floor, and we're able to collect the urine. Now, the one challenge we faced early on was that, surprisingly, I would say, Arizona State University does not allow waterless urinals. And that's because waterless urinals do have sort of a reputation of not functioning because of these issues I've discussed. So we had to first do this study with pint flush urinals. And although a pint flush is small from, say, a water conservation point of view, it still sort of doubles or triples the amount of urine you're collecting, and it's undiluted urine. So it's not ideal, but it was a starting point. And so I had a student look at this, and she did a lot of sampling of this system to really try and understand its dynamics. And the key take home here was, the total ammonia nitrogen to total nitrogen ratio was essentially 1 throughout this system. We were not able to control the urea hydrolysis in this system. I think for a variety of reasons, the sort of the dilution, the hydraulics, probably some biofilm development, we were collecting an ammonia solution. And sort of given the scope of her PhD, then we kind of shifted to just, can we take this, what we call hydrolyzed urine solution, process it through some, multi-process approach and sort of get maximum nutrient recovery. None of these processes alone, struvite, ammonia stripping, evaporation, are novel by any means. But at this time with urine processing, no one was taking an integrated approach to total nutrient recovery. So we had then this sort of mini resource factory in this building, right, where it's urine being captured from this building and going through these unit processes to create a phosphorus product, create a nitrogen product, create a potassium product. You could plug in your process of choice, but from a nutrient factory point of view, it was very exciting. And then that brings us to our current work and work that Lucas is leading, which is we've now been able to implement this building with waterless urinals. And we've been able to implement the acid dosing as well. As part of that, we've taken a bigger view of this project. We've done stakeholder work, looking at maintenance staff, other sort of technical staff within this sort of ecosystem, trying to understand barriers. So there's been technological barriers pointed out, sort of social, regulatory, economic, a lot of barriers, a lot of things kind of against what we're trying to do. But we find those to be sort of motivational. And, so there's things like plumbing codes. I'm working with a bigger group that's trying to update plumbing codes to allow this. The economics, I think Jonas touched on this. I mean, the economics of recovered products still aren't quite there. So there's a lot of work to be done on that as well. One of the first things Lucas did, now that we have some ideas of how we think it can be implemented in buildings, the question was, well, what type of buildings? And so Lucas did an analysis of major commercial and institutional building types. You can see restaurants, office buildings, through schools, airports. And we tried to calculate both phosphorus recovery potential and water savings because, depending on the setting, the water savings could be just as valuable as the nutrient recovery potential. So you have things like airports and universities that show tremendous potential for both nutrient recovery and water savings. So that's what Lucas identified. And then the question is, well, how do you implement this? So Lucas took just sort of a section of Phoenix and thought through different types of sort of decentralized or distributed wastewater treatment. And what we identify here are you can have individual entities like an airport, which could make sense to do the urine separation on its own. You can have universities or schools where you have a collection of buildings where it could make sense to urine diversion. And then you have places like office parks. So we have different sort of, it's not just fully centralized or fully decentralized. There's this continuum. And this is kind of what we're working through in terms of which types of locations in the community make sense to implement this. Just a few slides here to wrap up. So this is very current work from Lucas, which is doing the urine collection in this 5-story building. And again, we're constantly interested in occupancy because buildings are like kind of living organisms in terms of the people who occupy them. And so one thing that's really interesting if you think about a university is universities typically have sort of a normal occupancy phase and a below normal occupancy phase, whether it's holidays or summer. And under sort of baseline conditions of not trying to manipulate not trying to manage, say, urea hydrolysis, we see the dynamics play out in that during times of normal occupancy, when more people are around, more people are urinating, we can recover higher amounts of phosphorus than below normal occupancy phases, because that's that sort of extreme I talked about of fewer people adding urine to the system, longer hydraulic residence times, more phosphorus loss. So that's sort of the two baseline scenarios. And then on top of both of those scenarios, we overlay the acid addition. And so we built just sort of simple devices of a small reservoir, a small pump, adding acid into the urinals, I think on a schedule. And we in the lab work with acetic acid, but from an environmental health and safety point of view, we then transition to cleaning vinegar, right, which is like 5% acetic acid. So that is much more compatible with sort of a public space. And what we were able to do on the left was for periods of time, it still is challenging, but for periods of time, we're able to maintain a lower pH. And then on the right here is the urea to TN ratio. And again, during times when we had low pH, we were able to keep about 25% of the nitrogen as urea. Not 100%, that's something that's still kind of in works, but definitely we were able to eliminate any sort of maintenance issues and create the potential for either full urea recovery or partial urea recovery. Wanted to make a plug for a visiting scholar. He's been in the lab this past summer, again, looking at another integrated approach where he's trying to integrate nitrogen, potassium, and phosphorus recovery. His approach has been a combined nitrogen potassium product that has up to 3% by nitrogen, so a very high concentration nitrogen product, and then a phosphorus recovery. So in addition to the separation, collection, storage, we are interested in recovery technologies as well, and we see the most value coming from a total nutrient recovery perspective. So this is if you were to go around front, this is the oldest building at ASU. This is where it says Tempe Normal School, which is how ASU started a very long time ago. And the reason I love this building is because since it's so old, it doesn't have any bathrooms in it. The bathrooms for this building are the structure in the back. And for me, like, this is how I wish every building was designed, right? Because this is just asking for urine diversion. And you could really market it, right? It would be quite exciting to do. So a lot of text here, but essentially, where should we implement urine diversion? We should implement it in commercial and institutional buildings. And then within that category, there are certain types of buildings that make more sense in terms of how it's implemented in the community. How do we implement it? We believe strongly that you need to control the urea hydrolysis. Kind of all the good things happen once you can control the urea hydrolysis. So Something simple like cleaning vinegar allows you to control it. And then you can couple with that some total nutrient recovery. And then for the adoption, we're working with groups to implement updates to plumbing codes, trying to make the case for the value of nutrient recovery. This talk has been, say, mostly technical, but with all these technical pieces, there's a very strong non-technical piece. It's, building occupants, technical staff, like building managers and maintenance staff, all of them play an equally important role here. So thank you. Happy to talk more about this later. Thanks.